So in last slide, we developed a formula of chi-square with 1 degree of freedom in case of testing the two classes, phenotypic classes, and we tested the ratio 3 is to 1, whether the observer data is in agreement with this ratio or not. We developed this formula. Means A1 is the observed number of first class and A2 is the observed number of second phenotypic class. Then we can calculate the chi-square with this formula. If what happen? If this chi-square is significant, that is the calculated value is greater than the table value, then we can say that observed data do not follow theory of Mendel's law of segregation. Now we consider a case of say back cross. So now we consider the case of back cross in which F1 is crossed with the recessive parent, and we will get a ratio 1 is to 1 according to Mendel's law. But suppose A1 is my observed number in an experiment, A2 is my observed number of this class. When you cross A1 with AA, we will observe only two class and their expected ratio is 1 is to 1. Now A1 is the observed number of class capital A small a and A2 is the observed number of in class AA. And suppose there are total n individuals proceed. So you can say their expected proportion. Since we have only two classes and there are n individuals, so we expect that 50% belongs to first class and 50% belong to second class. So their expected numbers are n by 2 and n by 2. Clear? Then how you can compute the chi-square? Then chi-square as usual is computed by OI minus EI whole square divided by EI. If I substitute the value of OI and EI in this formula, since I have observed number say A1 for first class and these are the expected say n by 2, its square divided by n by 2, A2 minus n by 2 square divided by n by 2, and when I simplify this I will get, since this 2 comes here, I open the bracket A1 square plus n square by 4 minus NA. Actually, it is 2 NA1 by 4. It is when you open this, you will get A1 square plus n square by 4 plus 2 times A1 into n by 2. So this cancelled out. So I will get NA. Similarly, I will get this expression. I think it is very simple. Now, if I further simplify it, then I replace this A2 because A1 plus A2 is equal to n. So A2 can be written as n minus A1. So I just replace this A2 as n minus A1 and simplify it further. I will get A1 square plus n square by 2 minus n A1 plus A square A2 square minus n multiply by n. This is n square minus minus plus, so it is n A1. Now this cancelled out and ultimately what we get? Here n by 2 square minus n square. So if I simplify it, it is minus n by 2 square. So I will get this A1 square and A2 square. I further simplify it. A1 square plus twice, I multiply it, twice A2 square. Now this n can be replaced as A1 plus A2, its square. and divide it by 2. When I multiply this thing with 2, so this cancelled out. That's why 2 is not appearing here. So divide it by n. So it is twice a1 square plus twice a2 square and minus a1 square minus a2 square and minus twice a1 a2. And if I further simplify it, it will becomes a1 square plus a2 square minus 2a1 a2. This is nothing but a1 plus a2 whole square. So it is nothing but a1 sorry minus a2 whole square by n. So this is my chi-square. So in case of back cross, you just take the difference of two observed classes, square it and divide it by total number of observation. You will get chi-square with 1 degree of freedom. And if chi-square with 1 degree of freedom is significant, means the calculated value of chi-square is more than the tabulated one, then observer data will not follow the theory. Mean to say, the observer data does not follow this ratio. Clear? So if this chi-square at 1 degree of freedom is significant, then the observer data will not follow the theory. Now, we will talk about if we have two phenotype classes is there. Two phenotype classes is there means A dash means you can include AA and AA if A is dominant over A and AA is the recessive type. So A1 is the observed number of this class and A2 is the observed numbers in this class. Then in back cross, our expected ratio is 1 is to 1 and we will use chi-square as I have already mentioned a1 minus a2 whole square by n. If in case of F2, the phenotypic ratio is 3 is to 1 and we will use chi-square a1 minus 3 times a2 whole square divided by 3n. If you are expecting a ratio of 15 is to 1, then chi-square can be computed like this a1 minus 15 a2 its square divided by 15n is 9 is to 7. So you can write like that a1 minus 9 by 7 a2 whole square divided by 9 by 7 n. And if it is 13 by 3, so on the similar way, you can find out the chi-square a1 minus 13 by 3 a2 divided by 13 by 3 n. And if I generalize this result, if the segregation ratio is say L1 is to L2, then chi-square with 1 degree of freedom can be calculated by this formula A1 minus L1 by L2 A2 its square divide it by L1 by L2 into n. So if different ratios you want to test in two classes, then these are the various chi-square formula through which you can detect whether the linkage is there or not. Now we will talk about up to now we use a two allele at a locus. Now in case of double locus or double factor or two gene case, so in case of double locus, double factor or two gene case, we consider a cross like this as this cross has already been known to you. These are linked gene A and B, A and B, AB, AB, or this cross may be like this. Capital A, capital A, capital B crossed with this. So in F1 you will get this ratio, and in F2 gametes are produced, these four classes are produced in a ratio of 9 is to 3 is to 3 is to 1. But in case of back cross, the F1 ratio is 1 is to 1 is to 1 is to 1. Like so, in F2 generation, we have four gametes, the capital A, capital B, capital A, small a, capital B, and small a, small b. And their expected ratio are 9 is to 3 is to 3 is to 1. And suppose A1 is the observed number for this class, A2 is the observed number for this class, A3 is the observed number for this class, A4 is observed number for this class. Similarly, in case of back cross, our expected ratio is 1 is to 1 is to 1 is to 1. And suppose B1, B2, B3, B4 are the observed number of these classes respectively. Then observed frequency, or you can say ratio, is segregated with agreement with theory, can be again tested by chi-square. And formula remains same. Chi-square is given by I vary from number of times say k, number of classes k minus 1. So OI minus EI whole square divided by EI. Now, if if significant, if this chi-square is significant, then this class may be segregated as per theory. Number two, this class may not be segregated as per theory, and there may not be independent assortment of A, any A, B, any gene B. There may be linkage. So chi-square test is used for number one, thus to test the segregation of A dash A type segregation, B dash B type segregation, and chi-square L is used for testing of linkage. I think things are clear to you. Now we will do this in detail in say F2 generation. So in case of F2 generation, we will get chi-square with 1 degree of freedom in order to test the independent assortment like this. Then the formula is A1 plus A2 minus 3 times A3 plus A4, its whole square divided by 3n. And if I simplify this, I will get A1 plus A2 minus 3, A3 minus 3, A4 divided by 3n and its whole square. And second type class, we have 1 degree of freedom. In order to test the segregation of this, we will use A1 plus A3 minus 3 times A2 plus A4. And when I simplify it, it becomes A1 minus 3A2 plus A3 minus 3A4, its whole square divided by 3n. And in case of linkage, chi-square linkage can be tested by this formula. A1 minus 3A2 minus 3A3 plus 9A4, its whole square divided by 4n. But in case of back cross, chi-square for this segregation is B1 plus B2 minus B3 minus B4 whole square by 3n. Because In back cross, our expected ratio is 1 is to 1 is to 1. So these 3, 9, they replaced with 1. And similarly, chi-square with 1 degree of freedom for segregation of B and B, it is B1 minus B2 plus B3 minus B4 whole square divided by 3n. And for linkage in back cross, our formula is B1 minus B2 minus B3 plus B4 whole square divided by 9n. It is not 9n, I think it is, let me check. It is not 9n, it should be 3n. I'll check this formula and explain in next class. It should be 9 or it should be 3. I think it should be 3. It is not 9 or 9. Let me check. So now you should note in journal, if A dash A and B dash B is segregating with ratio say L1 is to 1 and L2 is to 1 respectively, then chi-square linkage is A1 minus L2 A2 minus L1 A3 plus L1 L2 A4 L1 L2 N for F2 generation. And in case of back cross, this journal formula is, I substitute A's by B's, like linkage B1 minus L2 B2 minus L1 B3 plus L1 L2 B4. It is L1 L2 N for back cross. So using this formula, you can detect the linkage or segregating if A dash A and B dash B is segregating under a certain ratio, or is there any linkage. We will use this formula to test the linkage. Then next part is estimation of linkage. Once we detect the linkage, our next part is we want to estimate this linkage. So the phenomena of linkage can observed in family, segregating for each of the two gene pair corresponding to two observed character. It means that at least one of the two parent involved in raising the family should be double heterozygous. Let us explain this in detail. So, first of all, you are very much familiar with linkage. What is linkage? Linkage happen when two factor or traits are inherited together because they are close to each other on the same chromosome. And in order to observe linkage, at least one parent in genetic cross must have both factor in mixed state, that is heterozygous. At least one parent should be heterozygote. Now, this heterozygosity is very much essential. If parents say capital A, small a, B, B, which is partially heterozygous, and other parent is small a, capital B, small b, which is again partially heterozygous, linkage cannot be observed. This is because neither parent is doubly heterozygous. So, at least one of the two parents involved in raising the family should be doubly heterozygous in order to find certain linkage. So, suppose this is my cross. In this case, capital A, capital B, small a, capital B, small b means none of the parent is double heterozygote. like this: capital A, capital A, capital B, small b. None of the parent is double heterozygote. So no information of linkage can be estimated because none of the parent is doubly heterozygote. Now consider another case. In back cross, what happens? We have F1, capital A, capital B, small b, is crossed with one of the parent, recessive parent, AABB. Now in this cross, this parent is double heterozygote. So the condition of double heterozygote satisfied, and it will give information about linkage. Another cross, say in F2. So A, capital B, small b is crossed with capital A, capital B, small b. Means selfing is there. Both the parents are double heterozygote, and our condition is at least one of the two parents involved. So both involved in this cross are double heterozygote. That's why it will give information about linkage. So based on the chromosome theory, linkage is nothing but it is theory of recombination fraction, which is represented by capital P. Theory of recombination fraction. Now, what is recombination fraction? Recombination fraction is nothing but it is the ratio of recombinants as compared to total number. You suppose these are my recombinant and these are the observed numbers, say, for these two recombinant. The ratio of A1 plus A2, and suppose n is my total number observed, then this ratio will give us the recombinance fractions. So now first we consider in back cross, we estimate linkage, we have to find out recombinant fractions. So in case of back cross, if we want to estimate linkage, then we have to find out the recombinant fraction. Say P, it is capital P. So let us start. What happens? We know that in back cross, capital F, no, sorry, this F1 is crossed with one of the recessive parent. That is, F1 is my double heterozygote. It is crossed with the recessive parent, that is P2. So you will get four types of phenotypes. If you will get this genotype, its phenotype is like this. If you get this genotype, then we will get this phenotypic class. If you get this genotype, we will get this phenotypic class. And if you get this genotype, we will get this phenotypic class. And suppose P is my recombinant fraction. Then how the value of these recombinant fractions in various classes can occur. So these are my four classes, phenotypic classes: capital A, capital B, capital A, small a, capital B, small a, small b. Right? Now in coupling phase, these two classes are of parental type. Then their recombinant fraction can be computed 1 minus p by 2 and 1 minus p by 2 here. And for recombinant type, these are the recombinant fractions, and these are for recombinants. In repulsion phase, it is opposite. It is p by 2, it is 1 minus p by 2, 1 minus p by 2, and it is p by 2. Now, in repulsion phase, these two are of parental type and these two are of recombinant type. I have already explained these things. Then again, we know that if we take the phenotypic classes, these are my phenotypic classes, I have already explained. So capital B, capital A, small a, capital B, and small a, small b. And if I get B1, B2, B3, B4, observed number for these phenotypic classes in such a way that their sum is say n dash. I mean to say it is B1 plus B2 plus B3 plus B4, it is n dash. And these are my expected proportion M1, M2, M3, M4. Since we are talk about proportions, so their sum will be equal to 1. These are the actually probabilities. Then their expected frequency. When probability is multiplied with the total number, you will get the expected frequency. So n dash m1, n dash m2, n dash m3, n dash m4 is my expected frequency. And in coupling phase, these are the recombinant fractions, which I have already. So you keep this thing in mind for further when we estimate the linkage in backcross. So what is the recombinant fraction in coupling phase and what is the recombinant fraction in repulsion phase? What are their expected proportion? What are their expected frequency? Using these things, we will develop a chi-square test or we will estimate these values, say recombinant fractions in F2 in case of backcross. So let us start. So we will use various method in order to estimate the parameter value, that is recombinant fractions. So there are 4 or 5 methods we will use for estimating these parameters. One of the most important method is maximum likelihood estimation method. Then we will discuss Emerson method, we will discuss product ratio method, we will discuss chi-square method also. So there are 4 or 5 methods. So I will explain the most important one, which is maximum likelihood method of estimation. So MLE is a statistical method which is used to estimate unknown parameter in a model. And using this model, we find the parameter value which maximize the likelihood function, which measure how well the model explain the observed data. And any estimator, or you can say maximum likelihood estimator in particular, possesses 3 important properties. First one is consistency. Consistency. Estimate approach the true parameter value as the sample size increases. Second one is its important characteristic is efficiency. Estimates have smallest possible variance among all unbiased estimators. And third one is sufficiency. The estimator uses all information from the data related to the parameter. So these are 3 important characteristic of an estimator which maximum likelihood estimator has. So in order to estimate the parameter, that is, or you can say recombinant fraction P, we have to form a likelihood function. So first of all, we will define what is likelihood function. So likelihood function for a set of observed data, the likelihood function, which is generally represented by say capital L, is defined based on the probability of observing each data point under a specific parameter, say P. So in our case, the data of backcross in F2 generation, the likelihood function is given by n dash divided by b1 factorial, b2 factorial, b3 factorial, b4 factorial into m1 raised to power b1, m2 raised to power b2, m3 raised to power b3, m4 raised to power b4. Now I will explain what is b1, b2, b3, b4, m1, m2, m3, m4, n dash. I have already explained it. So here B1, B2, B3, B4, they are nothing but they are observed counts for each category. Then M1, M2, M3, M4, they are expected probability for each category based on the unknown parameter P. And N dash, as usual, total number of observations. Now, question arises, why we use this formula? This might be possible that why we use this formula. So this formula is based on certain probability distribution. So it is multinomial distribution. Why we use multinomial distribution? So each offspring in backcross is independent observation. Number one, the joint PDF probability of observing a specific set of offspring with count say B1, B2, B3 and B4 follows a multinomial distribution. And this is the PDF of multinomial distribution. That's why I will use likelihood function as multinomial distribution. Then this formula seems quite difficult for because it involves powers and multiplication. So, in order to make it easy for estimating the parameter, what we do is we will take the log likelihood. We will take the log. So, log likelihood to simplify maximization work with natural logarithm of likelihood function, that is log L, because maximizing log L is equivalent to maximizing L. So we will take log on both sides. What I will get? Log of L. Now this all these things are not in, we are not interested in. We are interested in only say M1, M2. Sorry, this is C. If I consider this as say C, so C plus B1 log M1 plus B2 log M2 and this one, where C is a constant, right? Because n is fixed and b1, b2, b3, b4, they are our observed numbers. So they are fixed. So this can be treated as a constant. So you can write like that where c is a constant. Now, what happens? We will get the likelihood function. We will get the log of likelihood function in order to simplify the computation. Then what we do is, then we will get the estimating equations by differentiating the log the log likelihood function. How? So we get the estimating equation as curly log L over curly P and equating it to 0. Then take its second derivative and it should be negative. Now there are two phases. One is coupling phase and other is repulsion phase. So in case of coupling phase, what we will get? Our M1 is in coupling phase, this and these, they are parental type. These and these, they are recombinant type. So it is 1 minus P by 2. Please remember the last table. M2 is P by 2, M3 is P by 2, M4 is 1 minus P by 2. I substitute these values in place of M1, M2, M3 and M4 in log likelihood function. So I will get log L is equal to B1 log 1 minus P by 2 plus B2 log P by 2 plus B3 log P by 2 plus B4 log 1 minus P by 2. Is it clear? And now differentiate it with respect to P. So curly log L over curly P. Now B1, the differentiation of log X, you are very much familiar. It is nothing but it is 1 over X. Right? And you can say log of ax plus b d over dx. This is nothing but it is 1 by ax plus b into d over dx of ax plus b. So when you differentiate this function, so b1 is constant, b1 divided by this into differential coefficient of this. It is differential coefficient of minus p by 2 is 1 by 2. So I think this is clear to you. Similarly for this term, and lastly, you will get this term. Now you simplify it, and what we will get? It is B1 upon 1 minus P. How? Because this 2 cancelled with 2 and this minus is multiplied here. So B1 upon 1 minus P first term. Now in second term this cancelled with this. This is B2 by P. Similarly for this cancelled with this. This is B3 by P. And in this case, this minus goes here. So B4 upon 1 minus P. Now you take the LCM. If I take the LCM, I will get P into 1 minus P as LCM. So it is minus B times P plus B2 into 1 minus P because P is there. B3 1 minus P minus B4 P. So if I simplify this, what I will get? So if I simplify this, so it is minus B1P plus B2 minus B2P plus B3 minus B3P minus B4P. Now from this, we have P here, P here, P here, P here. So what I get if I take P common, or rather you can say minus P common, then what I get? From here I will get B1, from here I will get B2, from here I will get B3, from here I get B4. What I left with? I left with only two terms, that is B2 and B3 plus B2 plus B3. So if you simplify this expression, finally I'll get minus P into B1 plus B2 plus B3 plus B4 plus B2 plus B3. Now what is this? This is nothing. This is my n dash. And in order to estimate parameter, what we do is we equate this expression equal to 0 also. So the equating to 0, the above equation 1, then we will get, if I equate it to 0, what I get? The minus cancelled with this, or you can transpose this thing. This crossed with this becomes 0, and this term is taken to this side. I'll get P times B1 plus B2 plus B3 plus B4 is equal to B2 plus B3. And this is nothing but it is my n dash. So P times n dash is equal to B2 plus B3. So what is P? You can estimate P as B2 plus B3 upon n dash. Now in coupling phase, remember middle two classes are recombinant type and we are estimating recombinant fractions. So recombinant fraction will depend upon the observed data of recombinants divided by total number, which is the definition. And similarly, in case of repulsive phase, we apply the general knowledge. In repulsive phase, my recombinant observed values are B1 and B4. So B1 plus B4 divided by N dash is the estimate of P in case of in case of repulsive phase. So similarly, we can prove in case of repulsive phase P cap is B1 by B1 plus B4 by N dash. Then estimation of variance in backcross. So we can find the variance which is represented by V of P cap estimates variance, which is given as if I take the second derivative of log likelihood function and I divide it by 1 is divided by the expected value of the second derivative and taking minus side. So this will give us the variance. So we know that log L is the derivative we have obtained is this. Very simple. Now again differentiate it with respect to say P. So I will get curly square log L or curly P square. So in this case, it is 1 upon 1 minus x. You can find the derivative of this. This is nothing but it is 1 minus x square. Similarly, so these are the derivative. I think you are very much familiar with this derivation. Then simplify it further. When I simplify it, I will get this thing. If I take a minus common, then all the term becomes positive. And now I substitute this value in this expression. So variance of P is, since minus is there, so minus cancelled with minus 1 upon expected value of this thing. Now what is expected value of this thing? That is important. It is 1 upon B1 is nothing but B1 observed number. Its expectation is 1 minus P by 2 multiply by N in case of coupling phase. Divide it by this thing. These two are the recombinant type. Their proportion is this, and if I multiply this, and ultimately I will get this. So if you simplify this, you will get this expression. Or in simple way, 2p 1 minus p n dash p plus n dash 1 minus p plus n dash 1 minus p plus n dash p. And on further simplification, if I take n dash common from this, so this p cancelled with this p cancelled with this. So I left only with 2, this 2 cancelled with this. So ultimately I will get this. So this cancelled out and our variance of P is P times 1 minus P divided by N, which is the estimate of variance of P. So thank you very much. We will discuss other case in next class.